Okay, so this is our trig review. Remember, so measuring this height from the horizontal diameter in the units of the radius or with respect to the radius gives the sine of theta. So that'd be c over b, the relative size of c to b, or that height to the radius, which is where we get opposite over hypotenuse. And then cosine, it's the relative size of this length to the whole radius, in this case about 0.4, and that's where we get adjacent over hypotenuse, e over b. And then tangent is opposite over adjacent, which would be c over e. Okay, so I want to put up a bunch of identities that may prove useful in solving the problems. Okay, so here's those right triangle identities I told you about. Okay, and then the reciprocal 1 over sine, if you take 1 over sine, that's cosecant. So then that would just be the reciprocal, hypotenuse over opposite. 1 over cosine, again, the reciprocal of what cosine would be, hypotenuse over adjacent. And cotangent is 1 over tangent. So it would also be the reciprocal adjacent over opposite. Okay, there's that. Cosecant is 1 over sine. Secant is 1 over cosine. Cotangent is 1 over tangent. And then tangent, sine over cosine, and cotangent, cosine over sine. So those are all these are called the basic 6. And you know all the derivatives of these, right? So if you have to set up your function in an optimization problem using one or more of these, that's where your mastery derivatives, memorizing those comes in, because now you'll need the derivative. For instance, the derivative of secant is, remember? Secant times tangent, remember? Derivative of cotangent is? Negative cosecant squared. I heard lots of wrong offerings, okay? So don't forget. And then this is a really important one that shows up a lot. This is kind of the first identity, kind of the granddaddy of all identities, called the Pythagorean Identity. Sine squared plus cosine squared equals 1. And that comes from that triangle I showed you on the last. If the radius of your circle is 1, then that base there is cosine, and that height is sine. It's a right triangle, so by the Pythagorean theorem, you have cosine squared plus sine squared equals 1. You see that shows up in lots of problems using that. Okay, and then these are just versions of that. Solving for sine squared, solving for cosine squared. I do have a slight. Is this a minus? Thank you. Okay, so these will show up. So let's do a couple. Just do a couple setups of a couple optimization problems, since you have another set due on Tuesday, and they're a little bit harder, and they involve some trig. Some of them do, and they're harder, okay? They're round 2.
We're doing top hat.
No, we're done with top hat. Okay, here's a problem. It says, down at the bottom, in one part of an outdoor race, competitors come to a circular pond with a radius of 1.8 kilometers. They're coming this way in the race. It's like some kind of obstacle course or multi-event race. They come to here, and they got to make it here. And they can choose to run as far as they want to any point. We're going to call that point P, and then they can choose to swim. And so the pond's edge, though, is it's kind of rocky and uneven, so it's kind of hard to run on as an obstacle course. So one racer, Josie, can run 4 kilometers per hour on this terrain. Okay, so she can run 4 kilometers per hour, and then she can swim 3 kilometers per hour. How should she choose point P to finish this part of the race as quickly as possible? So she can run a little bit and swim most of the way. She could swim the whole way. She could run the whole way. Or she could run most of the way and swim like that. So how should she stop? Where should she stop running on the arc length and start swimming to best complete this part of the race, or complete this race as quickly as possible? All right, so we have, of course, we have a optimization problem. She wants to run this part of the race as quickly as possible. So this is a long and complex problem. So you have to have some kind of centerpiece, some kind of foundational point that you're not going to lose sight of in terms of the big picture. And what will that be? Okay, someone said a function. That's a good start. So you're going to have to write a function. No details yet, no math yet. Discuss with the person next to you. What's the general gist of that function? What's just the general? No math, no symbols. What will the general gist of that function be? Go. Here's the key. She wants to complete this part of the race as quickly as possible. What's the gist? This is all you need to focus on. What's the general idea of the function you need to create that will be what the whole problem revolves around? Okay, let's hear your ideas. Because this will kind of make or break whether you can really make significant progress on this problem. If you have this, can get this mindset. What is the general gist of the function? What's that? Okay, so he's saying it's a minimum. All right, so it has to do with finding a minimum. So what about this function then? Yeah. He's saying it has to output time. That's it. He got it. He nailed it. If you weren't thinking that, then you weren't paying attention Tuesday, and you were probably maybe not having a difficult time on the problems. You're trying to minimize the time. So you need a function that outputs time. And the whole problem is going to be building that function and using that function. Everything we do will be about this function. The function that outputs time, because we need to minimize the time. So a farmer wants to make a pen, and he wants to make it as the area as big as possible. What's the central focus of the problem? A function that outputs area. A function that outputs area. You're going to spend half the problem building that function and the other half the problem using that function. Okay, so a race car driver wants to achieve the fastest speed possible. What will be the central focus of the problem? A function that outputs speed. A function that outputs speed, and then we're going to try to maximize that function. Okay, so we want a function that outputs time. So let's just get the general structure of our time function. Again, really just what's the structure of the time function? Not looking at any numbers, not any symbols. In the broadest sense, how will we calculate the time? In the broadest sense, what will that time function look like? So it would be runtime, then plus swim time. So start easy. Make it easy on yourself. Don't jump in. Make sure you know what function your focus will be, and then get its overall structure. You know, if it's area of a circle, then just write pi r squared to start. If it's volume of a sphere, write out that volume formula to start with, and then get it into the form we need. So what do we need? We need time as a function of one variable, right? And so what would that variable be if it's about picking point P, right? So the variable thing here that changes, that results in different amounts of time is where she picks point P. So we need a quantity. We need a quantity that associates with where she picks point P. There's more than one choice. So what's a possible quantity that would determine that point P? Yeah. What distance? Okay, so the run distance. So it would be a run distance. If you knew the run distance, that would uniquely determine point P. Good. Another possible quantity that would uniquely determine point P. Okay, swim distance. Run distance would be a little more natural, right? Because it's where she stops running. What? Any other possible quantity that could pinpoint what P is? So think of this point, right? This arc length. What does that have to do with on a circle? Angle measure, right? Angle measure. So this angle measure from the terminal side or the initial side being B to the start, and then BP is your other ray. That measure of the angle right there would uniquely determine point P. Would you agree? So we want to write time as a function of theta. But the run distance and theta are almost the same, right? Because we said theta is arc length. It's just measured in the radius, right? So theta is just measuring that arc length with respect to the radius. So they're almost one and the same. Okay, so what about the time for the run? What will the general structure, how will we calculate the time for the run? How will we calculate how long it takes her to run that far? Distance times speed over speed. So distance of the run over speed of the run, right? And we'll call that speed. We'll call it V. That's S we usually use for arc length, so V for velocity, okay? And then the time for the swim will be the distance of the swim over the speed of the swim. Okay, so we're taking that general structure of the time for the run plus the time for the swim, and we're getting a little more specific here. To calculate that time, it will be the distance divided by the speed. And same with the time for the swim. Distance of the swim divided by velocity for the swim. And we need to get this all in theta. All right, so now we can use our trig. What's the distance of the run in terms of theta? How far does she go if she goes around the circle theta radians? Well, that's a number of radius lengths, right? Theta is the number of radius lengths.
Yes.
So how many meters is that if that's theta radius lengths? Yeah, the radius. So the radius is 1.8 kilometers. So theta is how many radius lengths she runs, and each radius is 1.8 kilometers. So the total number of kilometers would be 1.8 theta. Should make sense. What's the speed of her running? Given, 4. All right, so we got the time it takes her to run in terms of theta. We got it, 1.8 theta over 4. Okay, what about the distance of the swim? How are we going to get that? And we know that she swims how fast? 3, so that we just write the 3 down. So now, what's this distance of the swim? That's that red line from P to her destination. How are we going to get that? So, is there a triangle we can use here? Can you see the triangle that has this as its hypotenuse? Okay, so can you determine? So then if we can get it, if we know what that length is, And we know what that length is. See if you can do it. Take a minute and see if you can figure out those two lengths. Who knows their trig? Who knows their trig? Yeah, but you got to find A and B. So what are A and B? Okay, so from here to here is 1.8. How far is it from here to here? And then we got A. How far is it from there to there?
It's less than 1.
So look, we need the horizontal distance from the center to this point. What is that? What's the horizontal distance from here to here? That's cosine, but cosine would be measuring in terms of the radius. So the number of radius lengths from there to there is cosine theta. So how many meters is it from there to there? Why sine theta? How many meters is it from here to here if it's cos... Whoa. You guys, think before you talk. Think before you talk. This is how many radius lengths it is from here to here. That's cosine theta. So how many meters is it if this is the number of radius lengths? Or a fraction, this is like what? 0.75. It's about 0.75 of a radius length. And what's a radius length? 1.8 kilometers. Therefore, this length in meters is 1.8 times that 0.75, or 1.8 cosine theta.
1.8 times 0.75. That would be 1.35.
Remember, you're measuring, this cosine theta measures that distance in terms of the radius. It's about 0.75 radius lengths, and the radius is 1.8. So in kilometers, you would take 0.75 cosine theta of 1.8, the way I have it chosen here. So what's side A then?
1.8 plus 1.8 cosine.
Right, 1.8 plus 1.8 cosine theta. Okay, so now you should be able to get B. What is B? How many kilometers? 1.8 sine, right? So sine here is about 0.8. We want 0.8 of 1.8. So it's 1.8 sine theta. Therefore, C is? It's going to be the square root of 1.8 sine squared. Or let's do this. So 1.8 plus, right? Plus 1.8 sine theta, all that squared. All right, did I lose you?
No, you didn't.
How about the rest of you? So A squared, so A is that 1.8 over here, plus the 1.8 cosine theta, and this is 1.8 sine theta. So we've got A squared plus B squared equals C squared, and so C is the square root of the sum of the squares of A and B. A is 1.8 plus 1.8 cosine squared, or cosine, quantity squared, plus B is 1.8 sine theta, quantity squared. So this C right here is what goes here, the distance of the swim. C in the picture.
Why are both equal squared? Both
A squared plus B squared equals C squared. We're solving for C. Pythagorean theorem. Okay, so that would be it. That's the time, given the angle that she picks and the point. So given the point that she picks and the corresponding angle, this would calculate the time. So you'd have to take this formula here, the C formula, and put it right there. And now we've got that formula entirely as a function of theta. Okay, so that's kind of half the game, right? So we're half done. But this is the focal centerpiece of the problem. The function that outputs time reduced to one variable. Let's talk about the applicable domain. So what's the lowest meaningful value of theta and the highest meaningful value of theta? So theta can be as low as what? And what would that mean for her race? All swim, right? So if theta was 0, all swimming. So 0 is the lowest possible theta. And then what's the highest possible theta? Oh, lots of people saying pi. So this is pi over 2. This angle theta is pi over 2. And so then pi would mean what for her? Runs the whole way. So let's just talk through the rest of the problem. We're looking for the value of theta that minimizes the time. What are the possible candidates for the value of theta that would minimize her time? Okay, the endpoints, right? So we learned from last time, you got to check your endpoints. So we're going to find the time when theta is 0, meaning all swimming, and the time when theta is pi, meaning all running across the top of the circle. Any other candidates for the minimum time? Critical values, right? So, roadmap for the rest of the problem. We're going to find the critical values of our time function. And what are critical values? Well, the derivative is 0. So we're imagining a graph, this time angle graph, and we're saying maybe somewhere between 0 and pi, there's a low point, a minimum, a low point where the derivative would be 0, a local minimum. Okay? And so we're going to take the derivative and find critical values, and those will be possible. The ones between 0 and pi will be possible candidates. We'll check the critical values, we'll check 0, we'll check pi, and then we'll compare those times. The least time of all the critical values and the endpoint times, for 0 and pi, will then be whatever the least amount of time is, will give us the scenario that will minimize her time for this part of the race. Okay, so last semester I created a video of solving this whole problem, and I'm going to post that video for you to look at the rest. So I just wanted to set up the function and talk through the solution. But the video is, I mean, we would spend the rest of class finishing this problem, and I want to go on to something else, okay? So questions on setting up this function or where we would go from here? Any questions? Yes, sir?
I get lost with the estimation of 0.5 to 0.75 for like about 0.75.
I was just trying to give you, so for the point P that I picked, as radius lengths, that distance from there to there is about 0.75 of a radius length. Do you see that? It's about 3/4. So that would be what cosine would be, about 0.75. But we need this distance in kilometers. So one radius is 1.8 kilometers, so we need 0.75 of that for this particular point P. So if this is about 0.75, then this is about 0.75 times 1.8 kilometers. Because 0.75 is what fraction of the radius, right? And the radius is 1.8. So in kilometers, from there to there would be 0.75 times 1.8. Is it better? Is it better? It's about the meaning of cosine, right? The meaning of cosine is the distance from here to here as a fraction of the radius. But we need this in kilometers. We need from here to here in kilometers. So we're going to take that fraction of 1.8 kilometers. Because it's 1.8 kilometers from there to there, so we need 7.75 of that. So that's what that expression does.
Yeah.
Better?
Yeah.
Okay, cool. Other questions? All right. So just quickly, here's another problem. An A-frame barn is to be built so that it's 30 feet high, 40 feet wide, and 60 feet long. And we're going to build a rectangular room inside the A-frame. So this is 60. The height is 60. The total height from here to here is 60. And the total width is 30, so that means half the width is 15. Is that fair? 40, so 20.
20.
Okay, so the height is 60, half the width is 20 because the full width is 40. And we want to build this room in here. So we've got different possible scenarios we could pick. So we can get a real low, squatty room for a hobbit. All right, or a tall, skinny room for a shower or something like this. Or something in between, but we want the maximum size room. So this 60 feet long, you imagine that 60, did I do this wrong? It's 30 feet high, sorry. Right, this is wrong, right? You must think I'm infallible. Okay, 30 feet high. So the 60 feet, you imagine that's like going back behind the screen. So that's that third dimension. That doesn't change. So maximizing the volume of the room is really the same as maximizing the area of this pink rectangle. Would you agree? Because that 60 feet deep is just going to stay constant no matter how we do the numbers, right? So that's going to be a constant. So to get the maximum volume, we want to get the maximum pink area there, pink rectangle. So what's the central focus of the problem? Go. What's the central focus? What's this whole problem solution going to revolve around? Tell the person next to you. No numbers. Okay, what is it? A what? Function. That? Outputs. Okay, volume. You could do volume. Or we could just reduce it to, yeah, so you do area or volume. If you did volume, you just have the same thing as if you did area and then be times 60. Everything would be times 60. Or you can just omit the 60 and do area. So either one, a function that outputs area or a function that outputs volume.
So either one works, really?
Yes. So let's just start with the general structure of our area formula. What will it be? So general structure. It's a rectangle. Length times width. Okay? What's most convenient in this problem is to make our input variable not actually the length of the width, but this dimension here. The dimension from the corner out to the corner of the A-frame. So A in terms of x. All right, so we need to get the length in terms of x and the width in terms of x. Width first. That's easy. What's the width in terms of x? What's the width in terms of x? So get this width first and multiply by 2, right? What's that right there? From there to there is 20 minus x. 20 minus x is that. So then the total width is 2 times that.
Why is it easier to go from the outside x and not the inside?
We'll see in a second because of this next part, the length. It works, but it's a little bit easier when we get to the height. Okay, so now we've got a triangle, and we see an angle here. So do we want theta? No, because theta isn't changing, right? So here, this is involving triangles, but theta doesn't change. So it's not really about trig to get this height, okay? So because theta is constant. We're not changing the slope of the roof. We're leaving that constant. So this problem, although involving triangles, it doesn't really involve trig. So how are we going to get that height? Well, can you see? Here's this height relative to x, and here's 30 relative to 20. That's why this x is convenient, because what we're calling the length, or the height, over x equals what? By similar triangles. 30 over 20. So similar triangles is another thing that plays into these problems. Sometimes, like this one, it's most conveniently solved by similar triangles. And we want this height dimension, which is then 3/2 x. So that's this dimension. We got the width dimension. So what we're calling the length is 3/2 x. There it is. There's our centerpiece of the solution. It's the area of this dependent on how far we put the corner of the room from the corner of the A-frame, x. Did you catch it? Any questions? Please.
If we change the size of the closet,
Yeah.
it's still be the same thing.
Yeah, because it's dependent on x, right? The whole point is our formula is dependent on x. So if x is real small like this, we'll get a different area because we chose x differently. That's the idea of a function. Different inputs give different outputs, right? And so now what are we trying to do? We're trying to find the x that gives us the maximum output, the maximum area. So that's where calculus comes in now. What's our applicable domain? X could go from 0 to 20. So critical values, endpoints. Get all those areas. Find the one that's the biggest. Questions? Okay, so you got practice. Again, you're finding all these optimization problems are totally different contexts, different types of math tools that you're using, but they all are about that function that's going to output that quantity you're trying to maximize or minimize. That's always the focal part of that's what you're going to spend half the time defining and then the rest of the time using to solve the problem. Okay, so now we're kind of coming to the big conclusion of the course. So we need to kind of review where we were. We're going to totally change gears here for the last 10 minutes of this class. Not this one, this one. And we got to review the first part of class. Remember these pictures? So what did we do at the beginning? We looked at what situation? We looked at, you know what? You know how fast something's changing? And you want to know how much of it you have. Remember that? So actually what we're going to do in these we got today and then next week, we're going to kind of tie a bunch of stuff together in the whole course. So we have a kind of a big conclusion, a big idea of the whole course. So we need to go back and review from the beginning. You know how fast something's changing, right? Rate of change on the left. You want to know how much of it you have. So here's a scenario where our independent quantity, our x quantity, is the rate of change of elevation, is the miles from the border, okay? Distance from the border of some state. So how many miles from the border you are. And then the output here is how many 100 feet of elevation you get of change per mile. So it's a rate. It's a rate of 100 feet of rise or run per mile traveled. And then over here is just elevation, right? So just the accumulation of this rate of change of elevation would give you, how high you are from the border, or not how high you are above sea level. Sorry, the elevation relative to the border's elevation, okay? So 100 feet of elevation accumulated since you left the border. So rate of change of elevation, actual elevation relative to the border elevation. Okay, so let's have you talk and get your bearings straight here. Answer these questions. See if you can answer these questions. Work together. Yeah. Wait, what's it? Y doesn't equal k delta x. Delta y equals. That's not true. Delta y does not equal k delta x plus b.
Oh, x minus x minus.
You're so confusing. Yeah, you haven't said nothing you've said has been corrected. So this, are you using stuff that y-intercept? Yeah. No, that's not the y-intercept, right? The slope point would be x minus a plus b, where a, b is any point on the line. Why do people leave halfway through class? I don't ever get that. Why do people just leave in class? It's a little bit rude.
I guess they
Don't do that. Stay for class. Stay for class.
I know. It's impolite to do it. Inconsiderate.
That's right. That's right.
There's a question.
Okay, what's the big idea here? Anyone able to do it? We want the change in elevation from 0.8 to 2.2. How can we calculate that change in elevation? In fact, in two different ways. Anyone got one of the ways we could do that? Here's 0.8 to 2.2. So this question kind of embodies like the biggest idea of all calculus right here. That question right there brings to kind of just as a general idea behind the biggest idea in calculus, which we'll get to. It's called the fundamental theorem of calculus, okay? So what's one way to calculate the total change in elevation starting at 0.8 from the miles from the border to 2.2 miles from the border? Yeah.
A of 2.2
Okay?
minus A of 0.8
She wants A of 2.2 minus A of 0.8.
divided by
Oh, not divided. Just change in elevation. Just change in elevation, not average. Okay, so we could get the elevation, accumulated elevation at 2.2, which would be A of 2.2. Right? And the accumulated elevation at 0.8. And to get the change in elevation, it would be what? Subtract. So she got it. All right, now what about the other way? Yeah, how would we use that other graph? So that's using the right-hand graph, just the change in elevation, right? That's just the change in elevation between those two distances from the border. What about the other one? Yeah, Adam. No, we got big chunky intervals though.
Take the just use take k down to x for each one of those intervals.
Okay.
And add them all together.
Right. So remember, the change in elevation will be, so we take k1 times, what is delta x here? 0.4. The rate of change for those 0.4 miles times 0.4 will give a little change in elevation. Plus K2. All right, so so we could do that summation thing. And then what's going to happen? We're going to go dot, dot, dot until when? What's happening here with the 2.2? Partial interval, right? So we can do that for 5 intervals. So the last one we'll do there is 5 full intervals, or whole intervals. And then we'll need K6 times How much is that? This is 2 here. 2 starts that one. So half of a delta x, right? This is this idea of how does accumulation happen? Bit by bit by bit. And so we got all these whole intervals that we're summing up the bits of elevation, and then a partial interval. So, yeah, didn't I get it? Oh, sorry. So we're going to start with K3. Sorry. So it would actually be, let's see, I'll do it this way. So K starts with K3. Thank you. So K3, K4, and then not dot, 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 because this will be the last one, plus K5, and then K6 times the partial interval. Is that right now? Okay, cool. Quick. So now, delta x is 0.00004 miles. So now I've given you the new graphs. So delta x is really small, and we get this new rate graph, which is still a step function. Kinda, right? I mean, from the back, it doesn't look like a step function anymore. And then a much smoother elevation graph. Express the change in elevation 2 ways. We're going to just go a little bit, just a minute or 2 over, okay? So express the change in elevation 2 different ways now. When delta x is super, super, super small. Who remembers? Who learned something? Go. Now I'm calling that function e. So this is like the true elevation function. I'm calling it e now. And this is our function r. So we can still do e of 2.2 minus e of 0.8. That will give that change in elevation starting at 0.8 to 2.2. And then what? What about the side? How do we sum up a zillion little changes? Integral from 0.8 to of a bunch of little changes. How do we represent the little changes? R, x, dx. K delta x, right? But really tiny k delta x's. Starting at 0.8, ending at 2.2. So this idea of expressing this 2 ways, we're going to see on Tuesday, ties together the whole course. Ties together everything. Solving something like this brings together almost everything we've done the whole course.